Hello everyone, and welcome. I'm excited to kick off this presentation on measurement in physics. Today, we'll explore how we quantify the natural world around us. The title of our talk is simply Measurement in Physics, and we might also touch on some key concepts that help us understand the universe better. Over the next few slides, we'll cover fundamental principles, different types of measurements, and their importance in scientific discovery. Let's get started. Let's now look at slide 2, which covers the fundamental aspects of measurement in physics. First, we start with the basic concept, measurement in everyday life. This is something we do constantly, whether it's measuring the height of a door or the volume of water in a glass. In physics, precise measurement is crucial because it helps us understand and quantify the physical world accurately. Next, we explore the need for measurement in physics. Without measurement, we can't compare quantities, analyze phenomena, or develop scientific laws. It forms the foundation of all scientific inquiry. Moving forward, we see that units are essential for measurement. They give meaning to our numbers and allow us to communicate measurements clearly. For example, meters for length, kilograms for mass, and seconds for time. Speaking of units, there are various systems used worldwide. The most common now is the International System of Units, known as SI. It provides a standardized way to measure and report physical quantities. Now let's talk about the characteristics of good units. They should be well-defined, stable, and reproducible. This ensures consistency across measurements and experiments, which is vital for scientific progress. We also have specific physical quantities, like length, mass, and time, which are fundamental. These are the building blocks for all other measurements. To measure these quantities, we use various instruments, like rulers for length, balances for mass, and clocks for time. The precision of these instruments, indicated by their least count, determines how accurately we can measure. For example, the least count of a measuring instrument tells us the smallest measurement it can precisely record. This is important because it impacts the overall accuracy of our measurements. Finally, understanding the importance of measurement helps us appreciate how scientific knowledge is built, step by step, through careful, precise quantification of the physical world. This foundation supports everything else we will explore in this presentation. Sure, here's the word-by-word narrative script for slide 3. Today, we're going to explore some fundamental concepts in measurement. First up is mass, which indicates the amount of matter in an object. Think of it as what makes up the substance itself, regardless of its size or shape. When we measure mass, we're essentially quantifying how much stuff is contained within an object. Next, we have volume, which is used to quantify the three-dimensional space that a substance occupies. This means measuring how much space a particular object or substance takes up in our environment. Both of these measurements, mass and volume, are essential in everyday life. Whether you're cooking, buying materials, or even just understanding the properties of different objects, knowing how to measure these helps us make informed decisions. So, as we continue, keep in mind that understanding these basic measurements forms the foundation of many scientific and practical applications, tying into the bigger picture of how we understand and interact with the physical world. To understand any phenomenon in physics, we really need to perform experiments. And as you might imagine, experiments are only as good as the measurements we take. We measure a variety of physical properties like length, mass, time, temperature, pressure, and more. These measurements are crucial because they allow us to quantify what's happening in the physical world. When we try to verify laws and theories experimentally, accurate measurement is vital. Without precise measurements, we can't confidently confirm if a law holds true or if a hypothesis is correct. So, in essence, measurement is the backbone of experimental physics. It helps us turn observations into reliable data, which in turn helps us build and refine our understanding of the universe. Now, let's look at some common examples of physical quantities. For instance, the temperature of a room is 300 Kelvin. This number tells us how hot or cold the room is in a measurable way. Similarly, the length of a table might be 3 meters, giving us a clear idea of its size. The area of a hall could be 100 square meters, which helps us understand the space available. And when we consider the mass of a person, such as 65 kilograms, it provides a quantifiable measure of their weight. All these examples show how physical properties can be measured and described precisely using numbers. This is fundamental because it helps us communicate and analyze physical phenomena effectively within the broader scope of physics. Let's take a closer look at some common physical quantities. These are fundamental because they serve as the basic building blocks for all measurements in physics. For example, temperature, length, time, and mass are all essential quantities we use daily. What's important to understand is that these quantities are considered fundamental because their measurement does not depend on any other physical quantities. They are the starting points for defining other derived quantities. Recognizing these fundamental quantities helps us better understand how we quantify the physical world around us. Today, I want to talk about some common physical quantities that we often encounter and measure. These are known as derived quantities because they depend on one or more fundamental quantities for their measurement. For example, we have quantities like force, volume, speed, and area. Each of these is derived from basic physical quantities such as mass, length, and time. Force, for instance, depends on mass and acceleration, while volume is related to length measurements in 3 dimensions. Speed is derived from distance and time, and area involves measurements of length in 2 dimensions. Understanding these derived quantities is important because they help us describe and analyze physical phenomena more comprehensively. They connect fundamental concepts to real-world measurements, making it easier to understand how objects and systems behave. So, in essence, these quantities give us a more complete picture when studying physics, linking the basic building blocks of our universe to the measurable properties we observe and use in everyday life. Let's take a closer look at some common measurement units. When we talk about temperature, we often use Fahrenheit or Kelvin. These are standard units that help us quantify how hot or cold something is. Moving on to mass, we typically use kilograms or pounds. Both are widely used, with kilograms being common internationally and pounds often used in the United States. For measuring time, seconds, minutes, and hours are the fundamental units. They help us keep track of duration in everyday life. When it comes to length, we have meters, feet, and inches. Each of these units is useful depending on the context, whether it's scientific measurement or everyday measurements like height or distance. Remember, the key point here is that the measurement of any physical quantity relies on a standard unit. These units provide a common language that allows us to communicate and compare measurements accurately. Let's take a closer look at the characteristics of units, which are fundamental to our understanding of measurement. First, they need to be internationally acceptable, meaning that regardless of where you're from, the unit should be recognized and understood universally. This helps ensure consistency in measurements across different regions and disciplines. Next, the units should be reproducible, so anyone should be able to produce or verify the same measurement under similar conditions. This ties into their reliability. The units must also be indestructible, durable enough that they don't wear out or change over time, maintaining their integrity for repeated use. Invariable is another key point. Good units stay constant and do not change, providing a stable standard. They should be of a suitable size, meaning they are practical, neither too large nor too small for their intended purpose. Well-defined units are crucial because they have clear, precise boundaries that everyone understands. This avoids ambiguity. Finally, the units should be of a suitable size, again emphasizing practicality and ease of use. All these characteristics together ensure that units serve as reliable, consistent standards, which is essential for accurate measurement and effective communication in any scientific or practical context. This system was first introduced in France and is also known as the Gaussian system of units. It's interesting because it uses a different approach to defining units compared to the SI system. The key idea here is that it's based on the centimeter for length, the gram for mass, and the second for time. These are considered the fundamental units in this system. By using these units, the CGS system offers a different way of measuring and expressing physical quantities. Understanding these units helps us see how measurement systems can vary and how they are tailored for specific scientific contexts. This ties back to our overall theme of how measurement systems are developed and adapted for different scientific needs. This system was also introduced in France, and it's commonly known as the French system of units. It's interesting to see how different countries develop their own measurement standards, and in this case, France adopted a system based on 3 fundamental units. These units are the meter for length, the kilogram for mass, and the second for time. They form the core of this system, making it straightforward and consistent for scientific and everyday use. Understanding these fundamental units is essential because they serve as the building blocks for all other measurements. By relying on these standard units, scientists and engineers can communicate more effectively across borders and disciplines. This system, also called the MKS system, standing for meter, kilogram, second, has played a significant role in shaping modern measurement practices. It highlights the importance of having a standardized system to ensure clarity, precision, and universal understanding in science and technology. This system was introduced in Britain and is also known as the British system of units. It's interesting because it's based on 3 fundamental units: the foot for length, the pound for mass, and the second for time. These units form the foundation of measurements in this system. When we talk about the FPS system of units, we're referring to these specific units that have historically been used in many engineering and scientific applications, especially in the UK. Understanding this system helps us see how different measurement systems are connected and how they influence the way we approach engineering problems. It's a key part of the overall picture of measurement systems we're exploring today. In 1971, the General Conference on Weights and Measures held an important meeting where they decided on a unified system of units for international use. This system is known as the International System of Units, or SI, which comes from its French name. The SI is designed to provide a standard for measurements worldwide, making science and commerce more consistent. It consists of 7 fundamental units, which are the basic building blocks for measuring things like length, mass, and time. Additionally, there are 2 supplementary units that help measure more complex quantities. Overall, the SI system plays a crucial role in ensuring that everyone is speaking the same measurement language, which is essential for progress and collaboration across different fields. Now, let's take a closer look at the 7 fundamental units that form the basis of all measurements in the SI system. These are the essential building blocks for understanding the physical world around us. First, we have length, which is measured in meters, symbolized as m. This is the most common unit we use for measuring distance or size. Next is mass, measured in kilograms or kg. This tells us how much matter is contained in an object. It's fundamental because it underpins a lot of what we know in physics and engineering. Then there's time, measured in seconds. Time is crucial because it allows us to understand the duration of events and change. Moving on, temperature is measured in Kelvin, K. Unlike Celsius or Fahrenheit, Kelvin is the SI base for temperature and is essential in thermodynamics and scientific studies of heat. The 5th fundamental unit is electric current, which is measured in amperes, or A. This unit is key in studying electrical circuits and technologies. Next, we have luminous intensity, measured in candelas, SEED. This unit helps us quantify the brightness of light sources. Finally, the amount of substance is measured in moles, mol. This unit is fundamental when dealing with chemical quantities and reactions. So these 7 units, length, mass, time, temperature, electric current, luminous intensity, and amount of substance, are the cornerstone of measurement in science. They help us quantify and compare all physical phenomena accurately, which is essential for advancing knowledge and technology. Let's take a closer look at the definition of the meter. The meter is essentially the length of the path that light travels in a vacuum during a specific time interval. That interval is exactly 1,299,79245, 8 of a second. What this means is that we are using the speed of light, which is a universal constant, to define the unit of length. By fixing the time interval so precisely, we ensure that the meter is based on a fundamental constant of nature, making it incredibly accurate and stable over time. This definition ties the concept of length directly to the properties of light, which plays a crucial role in our understanding of physics and the universe. It's a beautiful example of how our measurement systems are rooted in the fundamental constants that govern the cosmos. The kilogram is defined by a very specific physical object, the prototype cylinder made of platinum-iridium alloy. This cylinder is carefully preserved at the International Bureau of Weights and Measures, which is located in Sèvres, near Paris. Essentially, this object has served as the standard for the kilogram for many years. It's important to understand that this means the mass of this particular cylinder has been the benchmark for what we consider 1 kilogram. The key point here is that this standard is a tangible, physical object, which highlights how measurement standards can be based on a concrete reference. As we move forward in this presentation, we'll see how the definition of the kilogram has evolved beyond physical objects to more precise, universal standards. So on this slide, we're looking at a very precise measurement of time. 1 second is actually defined by the number of oscillations of light emitted by a cesium-133 atom. Specifically, it's the time it takes for about 9,192,631,770 oscillations to occur. What this means is that a second isn't just an arbitrary unit anymore. It's based on the consistent behavior of atoms. This atomic standard provides a level of accuracy that was unimaginable with previous methods. It's a cornerstone of modern timekeeping and helps us maintain synchronization across the globe. This slide highlights how fundamental physics informs our everyday concept of time, connecting the abstract measurement to the physical properties of atoms. It is used to measure plane angle, radian. Now, moving on to the next point, let's talk about 2 supplementary units. These are alternative ways to measure angles, which can be very useful depending on the context. Understanding these units helps us see the bigger picture of how angles are quantified across different systems. So, stay with me as we explore these concepts and see how they connect to our overall study of measurement and geometry. Now, let's look at how we measure solid angles. This is where the concept of the steradian comes into play. The steradian is the unit we use specifically for measuring solid angles. Unlike the degree, which measures angles in a plane, the steradian helps us quantify the 3-dimensional spread of an object or a direction in space. Think of it as the 3-dimensional equivalent of the radian. When we talk about the steradian, we're essentially describing how much of the space around a point is covered by a particular object or beam. This measurement becomes crucial in fields like astrophysics, radiometry, and even in designing optical systems, where understanding how light or radiation spreads in space is essential. So, whenever we need to describe how wide or narrow a beam of light or radiation is in 3 dimensions, we use the steradian as our standard unit for solid angle measurement. Let's go over some important rules for writing SI units. First, notice that a full stop should not be used after the units themselves. For example, we write 7 meter, 12 N, or 25 kg without a full stop at the end. Next, when writing the numerical value and the unit, there should be only one space between them. So it's 10 kg, 5 N, 15 M, not 10 kg, 5 N, or 15 M. It's also important to remember that the symbol for units named after scientists, like Newton, Kelvin, Ampere, and Coulomb, must be written in capital letters, N, K, A, C. However, for all other units, the symbols are written in small letters, such as M for meter, S for second, kg for kilogram, and seed for candela. And one more key point. The units themselves do not have plural forms. So we say 6 meter, 14 kg, 20 second, or 18 Kelvin, never meters, kgs, seconds, or kelvins. Keeping these rules in mind helps ensure clarity and consistency in scientific writing and communication. All right, let's take a closer look at the slide. Here, we see a comparison between molecules and bacteria. Molecules are incredibly tiny, and bacteria are larger, but still microscopic. This slide introduces us to practical units we use to measure length, especially when dealing with such minuscule objects. Understanding these units is crucial because it helps us grasp the scale of what we're studying in microbiology and chemistry. When we talk about molecules, we're often referring to measurements in nanometers, while bacteria are usually measured in micrometers. Recognizing these units allows us to communicate sizes accurately and understand the relative scale of different biological and chemical entities. So, as we move forward, keep in mind how these units help us see the microscopic world more clearly. Let's take a closer look at the building blocks of matter, starting with the nucleus. The nucleus is at the very center of an atom, and it's incredibly small but densely packed with protons and neutrons. These particles give the nucleus its positive charge and mass. Around the nucleus, electrons orbit in regions called electron clouds, which are much larger compared to the nucleus itself. Now, moving on to atoms, they are the fundamental units of matter. Everything around us is made up of atoms, whether it's the air we breathe, the water we drink, or the objects we use daily. Understanding atoms helps us grasp the nature of matter on a microscopic level. The slide also introduces 20, some practical units for measuring length. When we talk about measuring very small distances or objects, we need units that fit the scale. These units are crucial for scientists and engineers because they allow us to quantify and compare things accurately. Throughout the presentation, we've been exploring how science helps us understand the universe from the tiniest particles to the vast cosmos. Using appropriate units to measure length is fundamental in making sense of the world around us, especially when dealing with atomic and subatomic scales. Let's take a look at the distances between planets. When we talk about these vast spaces, it's helpful to have practical units to measure length. These units make it easier to understand just how far apart planets really are. For example, distances within our solar system can be incredibly large, so using familiar units like kilometers or miles helps us grasp the scale. Understanding these distances also highlights the immense size of our universe and the importance of accurate measurement in astronomy. As we continue exploring, keep in mind that precise measurement is key to understanding the universe's structure and our place within it. Now, moving on to slide 24, which focuses on the distance of stars. When we talk about measuring the vastness of space, one challenge we face is that stars are incredibly far away, making direct measurement difficult. To tackle this, astronomers have developed practical units for measuring length that help us understand these enormous distances. These units are essential because they simplify the way we communicate and calculate how far away celestial objects are. Throughout this presentation, we've seen how different units are used for different scales, from everyday measurements to cosmic distances. Recognizing these units and understanding how they relate to each other is key to grasping the scale of our universe. So, this slide sets the stage for exploring the specific units astronomers use to measure the distance of stars and other celestial bodies, helping us better comprehend the universe's vastness. All right, let's talk about some practical units we use for measuring length in astronomy. First, we have the astronomical unit, or AU for short. This is roughly the distance from the Earth to the Sun, about 150 million kilometers. It's a handy way to express distances within our solar system. Then, we have the parsec, which is a bit more complex. 1 parsec equals about 3.26 light years, or roughly 30.9 trillion kilometers. The parsec is based on the method of parallax, which helps astronomers measure the distance to nearby stars. These units are important because they give us practical ways to comprehend the vast distances in space. They connect our everyday measurements to the enormous scales of the universe. So, understanding these units helps us make sense of the cosmos and how far things really are. Now, let's look at some practical units for measuring mass. When we talk about common items like grains or steel bars, it's helpful to understand the units used to quantify them. For instance, a metric ton, which is often used in large-scale industries, equals 1,000 kilograms. That's a huge amount of mass, often used in shipping or large-scale manufacturing. Then there's the quintal, which is less common in some regions but still important. 1 quintal equals 100 kilograms, making it a convenient unit for farmers and traders when dealing with crops or livestock. Understanding these units helps us communicate quantities clearly and efficiently, especially in contexts where precision matters. This knowledge ties into our overall theme of understanding measurement systems and their practical applications in everyday life and industry. Now, let's take a look at some practical units we use for measuring mass. Starting with newborn bobbies, they typically weigh about 1 pound. To put that into more familiar terms, 1 pound is approximately 0.454 kilograms. This helps us understand weight in different measurement systems. Next, consider a slug, which is a unit used mainly in the United States for measuring mass. A slug weighs around 14.59 kilograms. When we compare these units, we see how different systems have their own specific measurements, but they all help us quantify mass effectively. Understanding these practical units is important because it connects the abstract concept of mass to real-world objects, making it easier to grasp and relate to our daily experiences. This ties into our overall theme of understanding measurement and units in a practical context. Let's now turn our attention to some of the most fascinating objects in the universe: massive black holes. These are incredibly dense regions of space where gravity is so strong that nothing, not even light, can escape. When we think about measuring such enormous objects, we need practical units that help us grasp their scale. Throughout this presentation, we've looked at different ways to quantify mass, and these units are essential for understanding the vastness of the cosmos. Black holes, in particular, can have masses that range from a few times that of our Sun to billions of times more. Recognizing these units allows us to compare and appreciate just how massive these objects really are. It's a perfect example of how the universe challenges our sense of scale and pushes us to develop new ways of measuring and understanding the universe's most extreme phenomena. Let's take a closer look at the fundamental quantities that make up our understanding of the physical world. On this slide, we see the 7 basic dimensions that form the foundation of all measurements. First, we have amount of substance, which is crucial for understanding quantities like number of particles or molecules. Next, time, which is fundamental for describing how processes unfold and change. Moving on, we see the dimensions for length, mass, and temperature. These are probably the most familiar since they relate directly to everyday measurements. Then, we have luminous intensity, which helps us quantify brightness or light output. Current or electric current is essential for understanding electrical phenomena. And finally, there's the dimension of electric charge, often represented as the number of elementary charges. These 7 dimensions, length, mass, time, temperature, luminous intensity, electric current, and electric charge, are called the fundamental or base quantities. They form the core from which all other physical quantities are derived. Understanding these dimensions helps us see how everything in our universe is interconnected through measurement. This is a key part of our overall theme, understanding the structure of physical laws through these fundamental building blocks. The powers of fundamental quantities in a derived quantity are called dimensions of that quantity. In other words, when we look at a physical quantity, it's often made up of basic quantities like length, mass, and time, each raised to some power. These exponents, or powers, tell us how much of each fundamental quantity is involved in defining the derived quantity. Understanding these dimensions helps us grasp the underlying nature of physical quantities and how they relate to each other. It also plays a crucial role in checking the consistency of equations and in converting units. So, essentially, the dimensions of a physical quantity reveal the fundamental building blocks that make up that quantity, linking it directly to the core quantities of our physical universe. Let's take a look at some key uses of dimensions. First, dimensions are essential when we need to derive a formula, because they help us understand the relationships between different physical quantities. Second, they are crucial for converting units, ensuring that measurements are consistent and accurate across different systems. And third, dimensions are very important when checking the correctness of an equation, as they help us verify that both sides of the equation are dimensionally consistent. Overall, understanding these uses highlights how fundamental dimensions are in ensuring our calculations and formulas are reliable and meaningful in physics and engineering. Now, on this slide, we're looking at how to check the correctness of our equation. The key point here is that the dimensions of each term in the equation are the same. This is really important because it means the equation is dimensionally consistent. When we say it's dimensionally correct, we're confirming that the units on both sides match up properly. This is a quick and effective way to verify that our equation makes physical sense before we even do any calculations. Remember, ensuring dimensional consistency is a fundamental step in validating our equations, and it ties back to the overall theme of building reliable, accurate models. So, always check the dimensions. They're like a first line of defense against errors in our equations. Now let's look at how the time period t of a simple pendulum depends on two key factors: the length L of the pendulum and the acceleration due to gravity g. You can see here that t is influenced by these variables. To simplify our analysis, we assume that a constant k exists, which is dimensionless. This helps us focus on the relationship between t, L, and g without unnecessary complexity. Understanding this dependence is crucial because it forms the foundation for deriving the formula for the pendulum's period. By examining how these variables interact, we can better grasp the underlying physics governing oscillations. This sets the stage for developing an explicit mathematical expression that accurately describes the period. The smallest value that can be measured by the measuring instrument is called its least count or resolution. Essentially, this is the smallest increment that the instrument can detect or measure accurately. Understanding the least count helps us recognize the precision of the instrument we are using. The smaller the least count, the more precise the instrument is, allowing us to measure finer details. This concept ties directly into the overall theme of measurement accuracy and precision, which is fundamental in scientific experiments and engineering. So, always pay attention to the least count of your measuring tools to ensure your measurements are as accurate as possible. Let's take a look at this slide. The least count, which is the smallest measurement that a particular instrument can accurately measure, is 1 millimeter. This means that the ruler scale we're examining can measure lengths with a precision of 1 millimeter. Now, the ruler scale itself is a common and straightforward measuring instrument, but understanding its least count is crucial for accurate measurement. When we talk about the least count of length measuring instruments, we're essentially discussing the smallest unit that instrument can reliably record. Recognizing this helps us determine the precision and limitations of our measurements, which is vital in any technical or scientific work. So, in summary, knowing the least count of our measuring tools allows us to understand how precise our measurements are. And in this case, with a least count of 1 millimeter, we're working with a fairly precise standard. All right, so on this slide, we're looking at the least count of a vernier caliper, which is 0.1 millimeters. Now, the least count is essentially the smallest measurement that the instrument can accurately measure. In this case, it's 0.1, meaning any measurement we take with this caliper can be precise up to 1/10 of a millimeter. This level of precision is quite useful in many applications where small differences matter. Remember, the vernier caliper is a versatile and commonly used tool for measuring dimensions, and understanding its least count helps us interpret its readings correctly. This concept ties into the overall theme of measurement accuracy and precision in scientific and technical work. Today, let's look at the least count of length measuring instruments, which is 0.001 millimeters. This value indicates the smallest measurement that the instrument can accurately determine. Now, focusing on the screw gauge, a very precise instrument used for measuring small lengths and thicknesses. The least count of a screw gauge is crucial because it tells us how fine the measurements can be. In this case, with a least count of 0.001, the screw gauge can measure very small differences in length. Understanding least count helps us evaluate the precision of any measuring instrument, which is essential in experiments where accuracy is key. This concept ties into our overall theme of understanding measurement accuracy and the tools that enable us to achieve it. Let's take a closer look at the spherometer, a useful instrument for measuring the curvature of spherical surfaces. The least count of this instrument is 0.01 millimeters, which means it can detect very small differences in measurements. This high precision is crucial when working with delicate or precise spherical objects. The spherometer essentially helps us determine the radius of curvature by measuring the height of the arc or the depth of the spherical surface. Its design typically includes a circular scale and a screw mechanism for fine adjustments. Overall, understanding how to use the spherometer and interpreting its readings accurately plays a vital role in fields like material science and engineering, where precision measurements are key. Today, let's focus on the concept of least count, which in this case is 1 gram. The least count is essentially the smallest measurement that a weighing scale can accurately detect. It's a crucial factor because it tells us about the precision of our measuring instrument. When we talk about a weighing scale with a least count of 1 gram, it means the scale can measure weights in increments of 1 gram, and anything less than that might not be accurately recorded. Understanding the least count helps us evaluate how precise our measurements are, which is especially important in scientific experiments or when precise weight measurements are necessary. So, in summary, the least count of 1 gram indicates the smallest weight difference that our scale can reliably measure, and this concept applies broadly to all mass measuring instruments. Now, let's look at the least count of this electronic balance, which is 1 kilogram. The least count is essentially the smallest measurement that the balance can reliably indicate. In this case, it means that the balance can measure weights in increments of 1 kg. This is important because it tells us about the precision of the balance. It's suitable for measuring larger quantities where high precision isn't as critical. Electronic balances like this are widely used in laboratories and industries where quick and reasonably accurate measurements are needed. Remember, understanding the least count helps us interpret the measurements correctly and ensures we're aware of the tool's limitations. This ties into the overall theme of understanding measurement tools and their appropriate applications. Today, let's look at the least count of a wristwatch, which is 0.01 seconds. The least count essentially tells us the smallest time interval that the instrument can measure accurately. So, for a wristwatch with a least count of 0.01 seconds, it means it can measure time intervals as short as 1/100th of a second. This level of precision is quite good for everyday use, allowing us to track time quite accurately in daily activities. When we talk about time measuring instruments, the least count gives us an idea of their precision. The smaller the least count, the more precise the instrument is. In the context of wristwatches, having a least count of 0.01 seconds highlights how advanced and precise modern watches have become, bridging the gap between everyday convenience and scientific accuracy. This understanding is important as we compare different instruments and their capabilities in measuring time accurately. Today, let's look at the concept of the least count, which in this case is 1 second. The least count essentially tells us the smallest measurement that our stopwatch can accurately record. So, when we say the least count is 1 second, it means that the stopwatch can measure time intervals as small as 1 second. This is an important point because it defines the precision of our measurement tool. If we're measuring something that changes rapidly, a stopwatch with a smaller least count would give us more precise readings. But for many experiments or timing activities, a 1 second least count is sufficient. Understanding the least count helps us interpret the accuracy of our measurements and ensures we're making reliable observations within the limits of our instrument's precision. In this example, we see that the measurement made by student B is more accurate. The mass measured by student A is 25.61 kilograms, while student B's measurement is 25.65 kilograms. The true value of the mass, which we rely on as the most accurate reference, is 25.67 kilograms. What this shows us is that student B's measurement is closer to the true value, indicating a higher accuracy. Accuracy, as we've discussed earlier, refers to how close a measurement is to the actual or true value of the quantity being measured. So, even though both measurements are fairly close, the one that's nearer to the true value, student B's in this case, demonstrates greater accuracy. This concept is essential because it helps us understand the reliability of our measurements and how well we are capturing the true value of what we're measuring. In this example, we see that the measurement made by student C is the most precise. If we look at the times recorded, student B measured 3.69 seconds, student C recorded 3.695 seconds, and student A got 3.6 seconds. The key point here is that the more precise measurement is the one with the least uncertainty, which usually means the one with the most consistent decimal places. In this case, student C's measurement of 3.695 seconds is more precise because it has more decimal places and reflects a finer level of detail. This highlights how precision is about the level of detail and consistency in our measurements, which is crucial when we're trying to get accurate and reliable data in experiments. Let's take a closer look at these measurements. The mass is 6.11 grams, and the speed is 67 kilometers per hour. Notice how the number of digits in each measurement tells us something important. The mass has 2 significant figures, while the speed has 3. So, what exactly are significant figures? They represent the total number of digits that are reliable, including all the certain digits plus the last digit, which is uncertain but still part of the measurement. This concept is crucial because it helps us understand the precision of our measurements. When we report or use these values, we need to consider how many significant figures they contain to avoid overstating the accuracy. Remember, the more significant figures we have, the more precise our measurement. But also, it's about being honest and consistent with the data we collect. This idea ties into our broader goal of ensuring accuracy and clarity in scientific measurements. Let's take a look at these measurements. A time of 12.76 seconds and a length of 1.8 centimeters. Notice how the number of significant figures tells us about the precision of each measurement. The time, 12.76 seconds, has 4 significant figures, indicating a fairly precise measurement. In contrast, the length, 1.8 centimeters, has only 2 significant figures, which suggests a slightly less precise measurement. Understanding significant figures is crucial because it helps us communicate the accuracy of our data. When we're reporting or calculating, we need to reflect the precision of our measurements properly, so we don't imply a certainty that isn't there. In this example, the longer number with more significant figures shows greater precision, while the shorter one with fewer figures indicates a more approximate value. This concept links back to the overall theme of accuracy and reliability in scientific measurements. Always remember, including the correct number of significant figures maintains integrity in your data reporting. Let's go over some important rules for counting significant figures. First, when converting units, it's best to use powers of 10 to keep things clear and avoid confusion. For example, 64 has 4 significant figures, 3.6 has 3, and 25.06 has 5. Next, terminal zeros that come after the decimal point are significant. So in 205, there are 3 significant figures. In 3008, there are 4. And in 600.005, there are 5. Zeros that are located between non-zero digits are always significant as well. For instance, in 1002, both zeros are significant. Now, if a number is less than 1, all zeros before the first non-zero digit are not significant. For example, 0.0045 has only 2 significant figures. Also, terminal zeros in a number without a decimal point are not significant unless specified by a least count or measurement detail. For example, 16 has 2 significant figures, but 160 could have 2 or 3, depending on context. Finally, all non-zero digits are always significant. So in any number like 6438, all 4 digits count as significant figures. Remember, these rules help us accurately represent the precision of measurements and calculations. Let's look at some examples to understand exact numbers better. If I have 45 students, 5 apples, or a cube with 6 faces, these are all exact counts. When we count objects, the numbers we get are exact because they come from a precise counting process. Similarly, there are other ways to define exact numbers. For example, a dozen equals 12 objects, 1 hour equals 60 minutes, and 1 inch equals 2.54 centimeters. These are considered exact because they are defined standards or precise conversions. The key point here is that exact numbers are either defined by a standard or the result of a perfect count. Because of that, they have an infinite number of significant figures. They're absolutely reliable. This reliability is important when we're doing calculations, as it impacts how we handle measurements and data throughout our work. Let's go over some important rules for rounding off a measurement. First, when the digit to be dropped is 5 followed by 0 or nothing, the way we handle it depends on whether the last remaining digit is odd or even. If it's odd, we increase it by 1. If it's even, we leave it as it is. For example, 53.35 rounds to 53.4, and 9.455 rounds to 9.46. Next, if the digit to be dropped is more than 5, then we raise the preceding digit by 1. For instance, 62.354 rounds to 62.4, 9.6552 becomes 9.66, and 589.51 rounds to 590. Then, if the digit to be dropped is 5 followed by digits other than 0, we also increase the preceding digit by 1. For example, 64.62 rounds to 64.6, 3.651 becomes 3.65, and 546.3 rounds to 546. Finally, if the digit to be dropped is less than 5, we simply leave the preceding digit unchanged. These rules help us decide how to round measurements accurately, maintaining consistency and precision in our data. Let's look at these examples to understand significant figures in calculations. In the first one, we have 19 minus 1.567 minus 14.6, which gives us 2.833. Since we're subtracting, we need to consider the decimal places. The least precise number here is 19, which has no decimal places. So we round our answer to no decimal places, making it 3. In the second example, we add 13.2, 34.654, and 59.53. The sum is 107.384. Now, because 13.2 has only one decimal place, we round our total to that same level of precision, which gives us 107.4. The key point here is that when you're doing addition or subtraction, your final answer should be rounded to match the number with the fewest decimal places in your original data. This helps ensure your calculations reflect the right level of precision throughout your work. Remember, this concept is essential for maintaining accuracy in scientific and technical calculations, which ties back to the overall theme of understanding measurement and data precision. Let's take a look at how we handle rounding in multiplication and division. In this example, we first divide 6.579 by 4.56, which gives us approximately 1.508. When rounding, we look at the number's significant digits, and here, it rounds to 1.51. Next, we multiply 1.5 by 3.67, and then by 2.986. This calculation results in 16.4379, which we then round to 16. Because we want our final answer to have the same number of significant digits as the least accurate number involved in the calculation, which in this case is 16 with 2 significant digits. The key takeaway here is that when you're working with multiplication and division, you always round your final answer to match the least precise measurement's number of significant digits. This ensures your results are both accurate and appropriately precise within the context of your measurements. Today, I want to talk about errors in measurement. So, the key idea here is that an error is simply the difference between the actual value of a quantity and the value we obtain when we measure it. In other words, whenever we measure something, there's always a small discrepancy between the true value and our measurement. This discrepancy is what we call an error. Recognizing and understanding these errors is crucial because they can affect the accuracy and reliability of our measurements. Throughout this presentation, we've emphasized the importance of precision, and understanding errors helps us improve measurement techniques and interpret data more effectively. Let's look at the different types of errors we encounter in measurements. First, we have random errors, which are unpredictable fluctuations that occur naturally during the measurement process. These errors can cause the results to vary slightly each time we measure, and they are usually identified through statistical analysis. Next, there are gross errors, which are significant mistakes often caused by human error, such as misreading a scale or recording data incorrectly. These are usually obvious and can often be corrected or eliminated once identified. Finally, we have systematic errors, which are consistent and repeatable inaccuracies that tend to skew results in a particular direction. These errors are especially important to understand because they can be minimized through calibration and proper technique, helping us improve the accuracy of our measurements. Recognizing and addressing these errors is crucial for ensuring the reliability of our data and the overall quality of our work. These errors arise due to flaws in the experimental system itself. The system typically involves three main components: the observer, the measuring instrument, and the environment. Each of these elements can introduce errors that affect the accuracy of our measurements. The key point here is that these errors are not random, but systematic, meaning they have a consistent source. To improve the reliability of our data, it's crucial to identify and understand the sources of these errors. Once we detect where they originate, we can take targeted actions to eliminate or reduce them. This process helps us enhance the overall precision and validity of our experiments, ensuring that our results are as accurate as possible. Let's take a closer look at the different types of systematic errors. First, we have environmental errors. These are caused by external factors like temperature, humidity, or atmospheric pressure that can subtly influence our measurements. Even small environmental changes can introduce consistent biases, so it's important to control or account for these whenever possible. Next, instrumental errors. These stem from the measuring devices themselves, calibration issues, worn-out parts, or inherent limitations of the instruments. They tend to produce consistent deviations in measurements, which is why regular calibration and maintenance are crucial. Finally, personal errors. These are introduced by the human element, such as misreading instruments, poor technique, or subconscious biases. Awareness and proper training are key to minimizing these types of errors. Overall, understanding these categories helps us identify potential sources of systematic errors and develop strategies to correct or reduce them, ensuring our data is as accurate and reliable as possible. These errors arise due to faulty procedures adopted by the person making measurements. When we're taking measurements, it's crucial that we follow correct procedures because any deviations can introduce inaccuracies. These personal errors often happen when the individual conducting the measurement is not careful enough or makes assumptions that aren't quite right. For example, improper handling of instruments, misreading scales, or even rushing through the process can all lead to errors. The key takeaway here is that many measurement errors are not just about the equipment itself, but about how we use it. Being meticulous and consistent in our approach helps minimize these kinds of errors, which is essential for getting reliable results. Remember, the accuracy of our measurements depends heavily on our own actions and procedures, so paying attention to detail is vital. These errors arise due to faulty construction of instruments. Essentially, when instruments are not built or calibrated properly, they can introduce inaccuracies into our measurements. This is what we call instrumental errors. These errors tend to be systematic, meaning they consistently skew results in a particular direction. It's important to understand that such errors can often be minimized or corrected through proper calibration and maintenance. Recognizing the source of these errors helps us improve the accuracy and reliability of our measurements, which is crucial in maintaining the overall integrity of our experiments and data collection. To minimize environmental errors, It's crucial to ensure there are no external magnetic or electric fields around the instrument. Even small magnetic or electric disturbances can interfere with our measurements, so we need to keep these fields as low as possible. Additionally, maintaining a constant temperature and humidity in the laboratory is essential. Fluctuations in these conditions can cause measurement drift and inaccuracies. To achieve this, we should make proper arrangements, like using temperature control systems and humidity stabilizers. By following these steps, eliminating external magnetic and electric fields and stabilizing environmental conditions, we can significantly reduce environmental errors that might otherwise compromise our data. These measures are vital for ensuring the precision and reliability of our experimental results. Let's now turn our attention to advanced experimental setups. These setups are crucial because they allow us to push the boundaries of what we can discover and understand in our research. When we talk about advanced setups, we're referring to sophisticated equipment and innovative configurations that enable more precise measurements and novel experiments. They often involve integrating multiple technologies to simulate real-world conditions more accurately or to explore phenomena at a deeper level. Highlighting the key points, these setups improve the accuracy of our data, reduce uncertainties, and open up new avenues for investigation. They also help us validate theoretical models under more realistic scenarios, which is essential for advancing the field. Connecting this to the overall theme, advanced experimental setups exemplify how innovation in methodology drives scientific progress. By continually developing and refining these setups, we not only enhance our understanding, but also set the stage for breakthroughs that can influence the entire discipline. Sometimes, by mistake, a person might use an ordinary electronic scale that doesn't have good sensitivity, especially when measuring very low masses. This can lead to inaccuracies because the scale isn't precise enough to detect small differences. However, careful reading and recording of the data can really help reduce these gross errors. For example, if someone reads a pressure gauge showing 1.01 Pa as 1.1 Pa, that small misreading can significantly impact the results. These kinds of errors often happen because of mistakes in how we use the instruments, how we record the data, or how we perform the calculations. Recognizing and minimizing these errors is crucial for obtaining accurate and reliable measurements. These errors happen due to causes that are unknown, and because of that, they are sometimes called chance errors. Since we don't know what causes them, we can't completely eliminate them. Instead, we focus on reducing these errors as much as possible. Additionally, we can estimate the size of these errors using certain statistical methods. This helps us understand the reliability of our data and the accuracy of our results, even when these random, chance errors are present. So, for example, imagine you're measuring the oscillation period of a pendulum, and you do this 5 times using a stopwatch. This simple scenario helps us understand the importance of error analysis in measurements. By taking multiple measurements, we can see how consistent our results are. If there's a lot of variation, it might indicate some systematic or random errors. Understanding these errors allows us to evaluate the reliability of our data and determine the best way to improve accuracy. This example ties into the broader theme of our presentation, which emphasizes the need for careful measurement and analysis to draw valid scientific conclusions. When we look at multiple readings, the key idea here is that taking the average of all 5 measurements gives us the most probable value for the time period. Essentially, instead of relying on a single measurement, combining them helps us get a more accurate and reliable estimate. This approach minimizes the effect of any anomalies or errors that might be present in individual readings. So, the mean value becomes a solid foundation for our analysis, ensuring that our calculations and conclusions are based on the best possible estimate of the true value. This concept ties into the overall theme of precision and accuracy in measurement, which is crucial for reliable results in our work. The magnitude of the difference between the mean value and each individual value is called absolute error. Essentially, it measures how far off a single data point is from the average. This is important because it helps us understand the variability or accuracy within our data set. When we talk about absolute error, we're focusing on the size of the difference, regardless of whether it's above or below the mean. It's a crucial concept in data analysis because it gives us a clear, straightforward way to quantify errors or deviations. By understanding absolute error, we can better evaluate the consistency of our data and make more informed decisions based on how much individual values fluctuate around the mean. Now, let's talk about the mean absolute error, or MAE for short. Essentially, it's the arithmetic mean of all the absolute errors we've calculated. In other words, we take each error, ignore whether it's positive or negative, and find the average of these values. This gives us a single, easy-to-understand measure of how far off our predictions are on average. It's a key concept because it helps us quantify the accuracy of our models in a straightforward way. Understanding MAE is crucial because it ties directly into the overall theme of evaluating and improving predictive performance. The most common way adopted by scientists and engineers to report a result is through clear and structured reporting methods. When we communicate our findings, it's essential to present them in a way that is both accurate and understandable. This often involves using standardized formats, like tables, graphs, and detailed descriptions, to make sure the key points are highlighted effectively. The goal is to make our results accessible so others can interpret and build upon our work. Remember, good reporting not only conveys what we found, but also helps maintain transparency and credibility in our research. Connecting these reporting practices to the overall theme of scientific communication emphasizes how vital clarity and precision are in advancing knowledge. The relative error is defined as the ratio of the mean absolute error to the mean value. Essentially, it helps us understand how significant our errors are in comparison to the overall size of what we're measuring. By looking at the relative error, we can get a better sense of the accuracy of our measurements or predictions in a normalized way. This concept is especially useful when comparing errors across different datasets or variables that have different scales. So, in the context of our presentation, recognizing and calculating the relative error allows us to evaluate the reliability of our models and data with a clear, standardized metric. Now, let's look at an example to understand this better. Suppose we have a percentage error calculated as 0.028 times 100. This simply means that the relative error, which is the ratio of the error to the actual value, is multiplied by 100 to express it as a percentage. And this is what we call the percentage error. It's a way to quantify the accuracy of a measurement or a calculation in a more intuitive form. Remember, the key takeaway here is that the percentage error helps us understand how significant the error is relative to the size of what we're measuring. This concept ties back to our overall theme of understanding and reducing errors in measurements and calculations. Least count error is the error associated with the resolution of the instrument. Essentially, it reflects how precisely the instrument can measure a quantity. The smaller the least count, the more accurate our measurement can be. It's important to understand that this error is inherent to the instrument itself, based on its design and calibration. When we're taking measurements, the least count helps us determine the smallest change that can be reliably detected. So, keeping this in mind, choosing an instrument with a suitable least count is crucial for minimizing measurement errors in our experiments or readings. Today, I want to talk about how errors behave when we perform different mathematical operations like addition, subtraction, multiplication, and division. Essentially, when we combine measurements or data, the errors from each source don't just stay isolated. They interact and follow specific rules. For example, when adding or subtracting, the errors tend to combine in a way that the total error is roughly the sum of the individual errors. But when we multiply or divide, the way errors combine is a bit different. It's more about relative errors, or the proportion of the error compared to the actual value. Understanding these rules is crucial because it helps us estimate the overall uncertainty in our calculations. This ties back to our main theme of measurement accuracy and precision, Knowing how errors propagate allows us to make more reliable conclusions from our data. So, keeping these combination rules in mind helps us better evaluate the reliability of our results as we perform complex calculations. Estimation is a rough calculation, which means it's not exact, but gives us an approximate value of something. This can be incredibly useful because it helps us make quick decisions or plan when we don't need perfect precision. Think of estimation as a way to get a sense of scale or magnitude without getting bogged down in details. Throughout this presentation, we've emphasized the importance of accuracy, but estimation reminds us that sometimes approximations are enough to move forward effectively. It's a practical skill that applies across many fields, helping us save time and resources while still making informed choices. Now, let's move on to estimating the number of flats in Dubai City. This is a critical aspect because understanding the scale of residential units helps us grasp the overall housing market and urban density. When we talk about flats, we're referring to the majority of housing units in high-rise buildings and apartment complexes that define much of Dubai's skyline. To estimate this number, we consider several key factors: the total built-up area dedicated to residential purposes, the typical size of a flat, and the occupancy rates. By analyzing recent development data and urban planning reports, we can derive a fairly accurate estimate of how many flats are actually in Dubai. This estimate isn't just about numbers. It connects directly to our broader theme of real estate development and market potential. Knowing the number of flats helps us understand the demand for housing, the potential for investment, and the scale of infrastructure needed to support such a population density. So, by estimating the number of flats, we're essentially quantifying Dubai's residential capacity and getting a clearer picture of its urban growth trajectory. Now, let's talk about estimating the volume of water stored in a dam. This is a crucial step in water resource management because understanding how much water is available helps us plan for various needs, from irrigation to hydropower. To do this, we typically rely on measurements of the dam's surface area and the water level, or head. By knowing the surface area at different water levels, we can develop a relationship or a curve that shows us how volume changes with water level. This is often called a reservoir storage curve. Once we have this curve, we can estimate the total volume of water stored by simply measuring the current water level and then referring to our curve. This method is practical because it allows us to make quick, accurate assessments without needing to physically measure every part of the reservoir. It's important to note that factors like sedimentation and evaporation can affect these measurements over time, so regular updates and calibration are essential. Overall, this estimation process is a key part of managing water resources efficiently and ensuring that we use our water supply wisely and sustainably. Thank you all for your attention today. Before we finish, I want to leave you with a quick note about estimating the size of things using orders of magnitude. To get a rough idea of a number, you can round the coefficient a to 1 if it's less than or equal to 5, or to 10 if it's greater than 5. This simplification helps us quickly estimate large or small quantities without getting bogged down in exact figures. The key concept here is the order of magnitude, which refers to the approximate size of something expressed as a power of 10. Understanding this allows us to communicate and compare vastly different scales efficiently. So, whether we're talking about the size of a cell or the distance between planets, thinking in terms of orders of magnitude makes complex numbers more manageable. Thanks again for your engagement, and I look forward to our next discussion.